Hey guys, this is Srini and you're watching Python tutorial videos on my YouTube channel Python for Microscopists. In the previous tutorial, I talked about grain size distribution analysis using a microscope image that showed a whole bunch of grains and potentially that came from some sort of an alloy that's polished or a rock sample. The same method could also be applied or extended to segmenting cells if you're a biologist. Now, let's actually jump into the code and have a look at it. So we started off by importing an image, of course, importing all our libraries, and then importing an image as a gray level image. And then we defined pixels to micron conversion ratio, or not ratio, a conversion factor, which is 0.5 microns. So each pixel is about 0.5 microns in this case. And the reason why I did this is at the end, I wanted to report the distances and areas in microns and square microns rather than pixels and square pixels. We took the input image and thresholded it using ORSU, and which actually separated the grain boundaries from the grains. And then we did a couple of morphological operations, erosion and dilation, to enhance this grain boundaries so we can create a good mask to separate the grain boundaries and the grains. Then we took that mask and created a labeled image using ndImage.label. And this labeled image is nothing but every object in this image is labeled, or every grain in this image is labeled as 1, 2, 3, 4, 5, and so on. And once it's labeled, then we can use a function called region props that's within measure, okay? And what this actually generates a whole bunch of measurements of our detected objects. And we chose to report area, diameter, orientation, major axis, minor axis, perimeter, minimum, maximum, and mean intensities of all the things that got generated. It actually calculates a few more, but I chose to report these. That's pretty much it. Then we created or opened a blank CSV file. And to that, the first row, we populated that with blank plus join prop list, which is nothing but it goes to area, puts a comma behind it, area, and then diameter, comma, orientation, and so on. So our first row is nothing but all of the names here. And then we went down here and said, okay, the first one, where we left blank, fill the label at that position, and the next position fill area, and the next position do all of these accordingly. But if it is area, multiply the value by pixel to micron squared, because we are converting this into a square pixel, square micron value. Okay, so this is exactly what we have done, and let me go ahead and run this so you can see exactly how the output looks like. This is great. All the grains are nicely, it's very colorful. So we tend to think that the result is great and amazing. If you watch it a bit closely, now you can see that there are a whole bunch of grains here that are colored in red, and they're kind of touching each other. The grains here all are in yellow. The grains down here in some dark purplish color over there. These are all light blue color touching each other. These ones, again, dark purple to brownish color, all touching each other. What this basically, actually the best example would be these two grains, right? Keep an eye on it and look at the grain boundary. It almost looks very porous. What that means is there are certain pixels that are connecting this grain with the other grain. So the program actually thinks that, hey, this is one grain. There is no well definition between these two. This is a big problem now. When we do our analysis, we get pretty wrong values. This may be like aspect ratio pretty long, because this, if you combine these two grains, it's a very long grain. But if you separate these two grains, they are almost circular. So it affects our results. How do we deal with this? So this is a place where we should introduce the term watershed segmentation. If you have used ImageJ or any other commercial image processing software, you probably heard the term watershed or may have used it. Even in MATLAB, you have Watershed. So this is a pretty common and very powerful way of segmenting different grains or different cells or different regions that are difficult to segment just by using regular thresholding approach. So what is watershed? For those of us who grew up actually not speaking English as the primary language, watershed may be a new term. So let's start by defining the English term watershed. So the dictionary defines this as the area of land that drains water into a common body of water. Okay, so what does that mean? If there is some water that's actually dropping right here, that water actually goes down here. So rain that falls here, that all the water goes and then just goes into this valley and then merges with this river or creek, whatever you want to call this. Okay, and here there is a watershed boundary. That means the water that's falling on the other side of this boundary is going to flow in the other direction. The water that's going to fall inside is going to go into this valley. Okay, same thing on this side. Watershed segmentation, what this actually does is, if you look at this image, again I pulled up the documentation from ImageJ. Again, you can Google search and find the best one that describes to your liking, but this is a great image. I like it because this directly correlates with what we were actually talking here. You see this line here, think of this mountain ridge line as these white regions up here. Okay, so if you drop water up here, they actually go and then go into this valley down here. Okay, they fill these valleys. So this way you can see all these mountain ridges connected, so you can clearly separate these individual grains. And how do we apply this in Python? Well, as part of OpenCV, of course, they have threshold, the regular, traditional thresholding. They also have watershed-based thresholding, where the inputs are input image and the markers. The markers, we have defined markers in our previous tutorial, where we say, okay, I know for sure this is grain. I know for sure this is my background, grain boundary. So these are the markers that you need to supply to this program, and any ambiguous regions, right? So a marked image and the image itself. Now, the output of this is going to be a separated watershed boundary, where the boundary pixels are labeled with a value of -1. Okay, so that's the output here. So let's go ahead and jump in to the code, and let's go ahead and write the new code. So before writing it, let me erase all the variables from the last run. Let me clear the screen so we have all the room we need. Okay, so I'm going to do some copy and pasting so we don't waste our time. Obviously we have done this exercise in the past using traditional approach. So let's go ahead and import all the libraries from the last time. We probably need them. And let's import an image, and this time I'm going to import it using an example I've used 2-3 tutorials ago, which is using OpenCV to convert an image from BGR to gray. Nothing wrong in importing image and then putting 0 in there, so we import it as a gray level image. This is a different way of doing things, so why not repeat it? And also, let's go ahead and copy our pixels to microns. Let's use the same pixels to microns. It's the same image that we're going to use, and let's also scroll down and use the same thresholding. Okay, so we are again performing an OTSU-based threshold. Remember, for watershed, we need to send a mask that has clear pixels of the grains, pixels of the grain boundary, and the ambiguous region. We need to define these. So I'm slowly getting there. The first step, I'm thresholding this, and the next step, let's actually perform not erosion and dilation, but let's actually do opening operation, which I believe is same as erosion followed by dilation. Okay, so let me copy the kernels right from here. I don't want to rewrite that. And then my opening equals to, this is part of cv2.morphology, I believe. No, this is, where are we looking at? Opening. Let me actually see, look at the documentation. We have this segmentation. Oh, I'm sorry. This is part of cv2.morphology. Let me go ahead and copy this from the documentation, okay? I thought opening is, oh, okay. anyway, let me not vocalize my every thought. So let's do this opening of one, and let's go ahead and look at this image. cv2.imshow, and let's show this opening image. But before that, I need to tell what it is. Label it opening image, let's say. Okay, and let's also not forget to put the wait key so it doesn't wait forever for us. So let's go ahead and run this. So when I run this, we should see, there you go, that's our image. And one thing I do not like about morphological operations is any little thing that you do. For example, look at this area right there. Okay, that area is exaggerated. In fact, in my original image, if I just go to thresh image, it's not that bad. Yeah, I mean, we do have some region there, but then by opening it up, it kind of exaggerated that. So at your time, just do maybe erosion and dilation, and use any other morphological operations to see if you can make things better. But for now, opening is fine. Let's go ahead and use this opening. Now, I paused there for a second because I was thinking about what do we do with the grain boundary pixels. If you remember, let's go ahead and run this other code again. If you look at this, if you do analysis of grain size distribution and everything, all the grains that are on the grain boundary, on the edge of this image, you're going to get only partial grains. So it's not going to be giving you good result, right? I mean, statistically, it puts your statistics off. So there is a way to ignore all these grains touching the boundaries, touching the edges, and only include the inside ones. And that's the reason I kind of took a pause thinking about shall we do this now or later? Let's actually do it later. Let me clear the variable so it's clean again. So let's wait before we do that. Okay. So what's the next step? So next step is let me see, grain analysis. Okay, we are doing watershed. So the next step is, once we have this opened image, or once we thresholded the image, this is an optional step, right? Opening this. So once we have the thresholded image, the next step is to identify the pixels that definitely correspond to the background and definitely correspond to the foreground. Let's start with the background because it's easy. So I'm going to call this sure background, okay, equals to cv2 dot, how do I know? I mean, I could have actually taken the thresholded image and only the ones and include only the grain boundary pixels as my sure background. But I'm not really sure if I thresholded it well enough to trust that. So I'm gonna dilate my grain boundary, the grain pixels a little bit, meaning I'm gonna close the grain boundaries a little bit to make sure I'm picking the background, the grain boundary pixels a bit more conservatively. That's the term I'm trying to see. So let's say cv2 dilate, and what do we want to dilate? This image, the opened image, right? I mean, I could have used the thresholded image, but since we want to use this morphological operation, I'm gonna use that. So it helps if you type it correctly. Okay. Opening, and using what kernel? We already have a kernel there, so let's just using that kernel. And finally, how many times? Let's see how it looks like with one iteration. So let's go ahead and look at sure background, and this is our sure background. Okay, so let's go ahead and run this, and there you go. These are the pixels where we know for sure that they are coming from our grain boundaries. Now, I'm not comfortable with this region. Maybe we should just use threshold, or I can just do 2 iterations and just use even fewer pixels. Let's see how this works out. Okay, I'm gonna do 2 iterations and take only the few pixels that I know for sure are background pixels for now. So now that we have sure background, let's how do we identify sure foreground? This technically should be easy, right? Because we do exactly opposite. Instead of dilate, we should do erosion. So if I do erosion 6 iterations, 7, 8 iterations, then the grains get smaller, and I know the center of the grain is for sure part of my grain. In fact, I naively did that as part of my practice run and realized that there are some small grains, and if I erode it like 4 times or 5 times, those grains are disappearing and I don't have any seeds inside that grain anymore. If I don't do that many operations, then I'm not really sure that if I'm really on the grain or some grain boundary. So we need a different approach instead of doing that. Nothing wrong with doing that, by the way. If your image allows you to be successful doing that operation. So for this, what we plan on doing is distance. Let me actually open this distance transformation. I got some documentation here, and you can Google search and find the documentation. And this tells you how to perform distance operation. But in summary, what distance operation does is it's actually it looks at it actually maps. I'm trying to find the right English terms here. It actually maps the distance from a given pixel to the nearest or to the closest boundary. When I say boundary, to the closest zero value. So if you have a very large grain, then at the center of that grain, you're very far away from the grain boundary, right? So your distance map wise, the center of the grain will have a very large value. Okay, the edge of the grain, very close to the edge of the grain, the value is a very small number because the distance to the black or zero pixel is very small. I hope this makes sense to you. Okay, so that's basically what distance transform does. So let's actually implement that in our code, and I have written it down right here. I copied it, looked at the documentation. Again, distance transform and most of these operations are available in multiple packages. I'm just trying to find out the ones in OpenCV if possible. So the input image for distance transform is our opened image right there. Yeah, opening image. And then the algorithm that we are going to use is cv2.dist_l2. Again, I haven't looked up the documentation to the depth where I can intelligently tell you exactly what this does versus what other one does. Go ahead and apply it and see if it works. If so, go ahead and use it. That's it. And 3, I believe, is the patch size, or the, let's go and see, it's the mask size. Okay. So 3 is our mask size right now. And if you're curious, you can actually look at the image distance transform. It should look very close to our dist_transform. Okay, it should look very close to the grain boundary image, and here it is. There you go. Although the values at the center are higher than the values over there, if you look at the distance transform right here, let me go ahead and close this. If you look at the distance transform, this is a float 32 type of number. Okay, or so this is I almost said float 32 type of integer. This is a float 32 type of number, same size as our input image. So we have distance transform. Now what do? I can take the entire distance transform image, but that doesn't make any sense because that would be kind of like taking our opened image. I'm going to put some threshold limit on my distance transform and say any value that's like up to 20%, I'm going to accept it. Everything other below that, I'm going to reject it, which is basically stay close to the center of the grain and ignore the pixels that are very close to the grain boundary. That's a way of saying it. So how do we do this? And obviously, I'm going to threshold it. And how do we threshold in OpenCV? This is cv2.threshold, right? But then I'm going to assign this to, it's going to return 2 values. One is this, and then the other one, instead of threshold, I'm going to call this sure foreground, okay? So it's going to return these 2. And what am I thresholding? I'm going to threshold this image that's distance transform, okay? So I'm going to threshold this image, and from where? I can do it from 0, but again, it doesn't make sense. So let's actually take 0.2, 20% of whatever the maximum value is. So dist_transform, right? Distance transform dot, you know what the maximum, how to get the maximum value, right? Dot max. So that returns, so this one is trying to find what the maximum value is, and then we are taking 20% and we are saying, okay, that's where my threshold is. And replace all the thresholded pixel by a value of 255, and that's none. So Now let's go ahead and do our shear foreground. Let's look at how our shear foreground image looks like. Let's actually convert this into 8-bit. Not 8-bit. Yeah, I mean integer. So let's say shear foreground equal to, did we import numpy? Yeah, np dot uint8, and we are converting our shear foreground. Okay, so now let's have a look at our shear foreground image, and there it is. Okay, so this hopefully should make sense. So this image is nothing but the regions in my original image where I know for sure the pixels correspond to the grains. All these other regions, I am not sure. I mean, we could have attained similar, we could have attained similar result by eroding the grain boundary region. But again, like I mentioned, that did not work when I tried, because some of these small grains kind of, I lost them when I did that. So anyway, so this is our distance transform. This is the best way of identifying this region, especially when you do this watershed type of segmentation. Okay, so now what? Because we have shear foreground, let's also define what my unknown pixels are. Okay, so my unknown pixels is nothing but this minus that. So cv2 dot subtract, again spellings, and what do we subtract? Shear underscore background minus shear foreground. So these are the pixels I do not know. So if you want to look at it, unknown, and this is unknown pixels. So let's run this. Something happened. So cv2 dot subtract unknown equals to subtract shear back. Oh goodness, I'm using subtract, so it should be that. Sorry about that. And let me drag this over here. So this is nothing but the inverse image of our shear foreground, right? I mean, these are the pixels where I do not know exactly what's happening. So watershed, go ahead and fill this. That's what we need to be doing as a next step. Okay, so watershed requires markers. So let's now define markers. Okay, so I think we're not skipping any steps. So unknown, and let me look at my notes. Yeah, the next step is, once we do unknown, we just need to define our markers. And how do we do the markers? There is something called connected components, and in OpenCV, again, we can pull up the documentation, but what it does is, again, as the name suggests, it's actually looking at all the connected components and then actually separating them. Yeah, if you have two grains that are kind of porous, with some grains that are connecting these two, then that's one entity. That's why it's very important for us to do this pre-processing step. Okay, so let's return. Did we return 2 before? Okay, let's by the way, we are not using these RET numbers. You may as well actually put underscore if you don't want to return anything, but let's just put RET3, and it stores it, and markers, and what is that equal to? So let me copy from the documentation here. cv2 connected components, cv2 dot connected components, and what's our input image? Shear foreground. Okay, so this is my input. So I'm actually creating a marker basically for my shear foreground there. Now, I mean, I supplied the shear foreground, so it actually looks at that. It looks at the non-foreground pixels, and now you have a value for that. So what we should do now is, by default, it gives a value of 0 to these. If you look at shear foreground, sorry, you see a bunch of 255s here, and you'll also see other values there. So what these are unknowns, actually, the 255s. So we should actually give them a value. So let's start with markers equals to markers plus 10. By default, the marker has a value of 0 here when we do this connected components. That means my unknown is also 0. not unknown, sorry, my background is also 0. So I don't want my markers to be mixed with my background. So I'm actually, this step may be confusing, but then try this a couple of times, print out the results, look at them, and then make sense out of it, okay? So all I'm doing is I don't want my markers to have a value of 0. I want them to have a value of 10. So I'm just adding 10 to these markers, that's it. So I defined my markers here, and I want my markers to have a value of 10, okay? So once we get that, then I'm going to say, by the way, markers is nothing but, oh, we haven't run this. Let's actually run it up to this point so you can see exactly. Okay, so this is the image we had before. So markers is nothing but an ND array. Okay, so within that array, we are saying we are adding these markers, a value of 10. And now let's actually look at markers of, let's say, unknown. If my unknown is equals to 255, okay, then my markers will have a value of 0. Okay, all 255s, okay, in my unknown, my marker value is 0. Okay, again, print it out, go ahead and look at it. So all I'm doing is creating a marker array where I have my sure positives with some value, sure negatives or sure background with some value, and this unknown regions with some value. That's all I'm trying to do. So here I created markers for sure foreground. My marker value, I don't want the marker value to be 0, so I just said markers is markers plus 10. And then my unknown equals to 255 for those pixels. My markers are all equal to 0. Okay, that's it. I think we have all the markers that we need. In fact, if you want to look at this, then go ahead and show. What is it? Let's just do markers. Let's say cv2.imshow. I'm just trying to see. I played with this before and I realized that one of these C maps actually, okay, so markers, this is what I was trying to see. If you just do markers, it's tough to see anything. Let's go ahead and do this. Okay, let's not show anything here and run, and you should see an image. It's tough to see anything happening over there, so that's why I actually put cmap equals to jet. A couple others also actually worked okay. I'm just changing this region, so even now it can be, if you zoom in, maybe you can see the 3 different regions. The colored ones are all these sure foregrounds. And then you should see like one region which is like completely background, and you would see better if you color it in jet. That's all I'm trying to say here. Okay. And by the way, I structured this tutorial based on a different tutorial that is part of, I believe, the documentation for Watershed or something. Again, I looked up 5-6 different sources, and then I'm putting everything into one. So if this sounds like some of the steps very similar to the documentation that you're reading right now, there is a reason, because I really am not trying to invent something new. Okay, I'm just following something that's already out there. So now let's, we are all set to actually, we did this, we did that. Now we are all set to actually do our watershed, and this is just CV2. Oh, it's actually, let me copy it from here. My markers now, it's going to do the filling, so let me paste it here. So my markers are updated by Watershed on, using my original image right there and the markers that we just created up here. Okay, so that's all. So let's go ahead and run this to make sure it is, yeah, so nothing wrong until now, so it seems to be fine. Let's go ahead and visualize this. So the best way, by the way, if you remember, in Watershed, look at the documentation. Oh, sorry, wrong one. Look at the documentation. The watershed boundary is in -1. So we should be able to overlay that onto our image and actually have a look at it. So the best way to look at this is in my image 1, okay, if my markers are equal to -1, okay, in my image 1, if my markers equals to -1, then what color should we color them? Then let's color them in yellow. I think blue, green, and red. Isn't green and red yellow? We'll find out. Okay, so my image one, so all I'm doing is in my image one, replace the pixels wherever there is markers with a value of -1, which is nothing but our boundary. Yeah, replace those pixels with a pixel corresponding to yellow color. That's pretty much it. Okay, and now let's have a look at it. So let's assign this to a different image. And color this, we have done it in our previous lecture. Color to label to RGB. This is a great function that actually takes label and colors it in RGB. And what is our input? Our input is markers. And let's put our background label equals to 0 black. Okay. Now, are we ready to look at it? Yeah, why not? cv2.imshow. And let's just call this overlay original image, and let's do image 1, right? And then let's also show image 2, cv2.imshow, and let's just say what is this, color.label to grain. So these are colored grains. Okay, and this would be image 2, and finally let us oh yeah, cv2.weight key 0. Okay, now let's run this code. Wow, that looks pretty good. Let me drag this other image from this other screen, put these two up here, and now hopefully you can see how well the segmentation is here compared to the previous segmentation that we have actually done. Yeah, so you can clearly see that here, you know, we had like a bunch of, this could have been better. In fact, that we did not identify. This wouldn't identify. Maybe we can change something and then identify these regions. But then some of these, most of these big grains, you know, very well separated compared to the previous approach. So again, you can play with a few of these parameters. A couple of parameters I would play with is, you know, this opening right there. And the other one I also would recommend is, remember the 20% distance transform? What happens if you do 50% of the distance transform and use that as your seed? If you do that, then our result looks very bad. Okay, so you see how the result looks pretty bad. So, experiment with this. What happens if I do 0.1? It may be the other end of the spectrum. Now I have way too many grains, and that's not bad. It looks very similar to the other one actually. So experiment with some of these and see how that does. But now I almost forgot that we have to take care of these grains that actually touch the boundaries. Okay, so how do we take care of those? So at any point after thresholding maybe, or after opening, this is not a bad place to do this operation. It's called ClearBorder. It's part of where is it, scikit image segmentation. So let me go ahead and import that library, that function ClearBorder, and instead of taking this opening image, I'm just gonna do opening. I'm overwriting my opening image because I'm too lazy to change the entire code. Clear_border, and our input image now is called opening. Okay, so all I did is imported this something called ClearBorder. Okay, that is nothing but edge removal thing. It's not a clear name right there for some reason. Anyway, and I'm overwriting my opening image just by clearing the border. Okay, so let's go ahead and run this and see how the result looks like. You see how it ignored all of these grains that are actually touching the boundaries. Okay, so if you do not want to include them, this is not a bad thing to add. Okay, that's pretty much it. This is how Watershed works. And if you really want to complete this, let's go ahead and copy the paste from the last time where we did our region props. So which is our, let me copy and paste it. Let me delete this. And once we have our image 2, we can use the, sorry, let me go ahead and do this. Our regions is nothing but region props on these markers right there. Okay, and intensity image equals to img. Again, the reason why we are supplying intensity image is because we want to calculate the intensities within each grain that we just separated. And the remaining, there is no point in me reinventing that. So let me again copy and paste the entire code here. There you go. All of this is, again, just to repeat, what I'm trying to do here is define a property list called area, diameter, orientation, and all of this, and then open an image, a file, .csv file in the write mode, and then the first column, sorry, the first row, I put grain number, comma, another placeholder, comma, and then area, comma, diameter, comma. That's what the join is doing here, okay? And then creates a new line. What happens in the next line? In the next line, the first thing it prints out is the grain number. I actually added this grain number equals to 1, so the first grain is going to be 1, number 1, and it's going to write down that number underneath this grain number. And then it goes inside this loop and enumerates the prop list, which is area, equivalent diameter, and for each of this, it's going to print the value, but not just the value. If it is area, it's going to multiply area by the square of my pixel to micron, because area is 2 dimensions, so you need to multiply by square. If it is orientation, multiply that by 57.2958, because that converts radians into degrees. If it is the intensity less than 0, what this means is prop.find intensity less than 0. What that means is if it is not minimum, mean, or max intensity, then multiply the value by pixels to micron value. Else, the only thing that's left is anything that has the name intensity in it, just print out the value, because we don't need to convert intensities into any of these other units. That's it. Now let's go ahead and run it. And everything seems to be successful, and it should be called image measurements.csv. Let's go ahead and look at it. Image underscore measurements written just now, and let me open that, and hopefully we should see a very nice table. Well, I'm opening it in Excel, so it takes 30 seconds. Let me drag it over here. Oops, there you go. So grain number, an empty space, area, and all of these parameters. Okay, that's it. And I hope you found this tutorial useful. And in fact, I started to think it would be more useful if we do the same exercise on hundreds of images, right? Who analyzes just one image to do grain size analysis? Maybe you have a stack of images. Maybe you have a folder that has 50 images and you want to run this over 50 images. So I'll do that in my next tutorial, because this one's almost 40 minutes now. And I personally watch only videos that are very short videos. But anyway, I hope you found this tutorial very useful. If so, please like this video. And if you like the content that you're seeing in this channel, please subscribe to this. It keeps me motivated to create more content. And let's meet again in our next tutorial, where I hope it would be a short one, where I take this and then show how to apply this to multiple images. Thank you very much and enjoy life.